All right. Доброе утро. Сегодня у нас две задачи. Первая – закончить capacitors. Вторая задача – начать новую тему – электрический ток, закон Ома. Anyone? No? Remember that feeling? Every time when you may read a textbook and you read such words like force, electric field, potential, energy. If you don't know the exact meaning of those words, that's exactly the feeling you feel. So if you do it at home, you have an easy fix. You can read the textbook, do the search, but 3 times during this semester, you will not be do any search except in your memory. So certain amount of memorization would help. And if you are a pre-med student, this is how much memorization you're going to expect in the future. This is how much memorization this course requires, just to keep it in perspective. And by now, I think you already have answered this question, right? We know a human brain has 2 halves, so you can use 1 half to listen and second half to think about the question and just enter your answers. Well, what is happening? I'm going to show you very soon. But of course, we also should use our imagination. We have a capacitor. And for us, a capacitor is just 2 plates parallel to each other, same size, certain distance, maybe some filament filling in between. That's it. It doesn't really matter how we build it. It could be circular, it could be cylindrical. There are many types of capacitors. It doesn't really matter. In this situation, we just have a simple model, parallel plate capacitor. And the power supply, normally just a regular battery, like this one. All we need to know about it, if it's a good battery, it keeps potential difference between the electrodes equal to the number we read on it. That's it. How does it do it? Who cares? So this is just a source of constant voltage. This is, again, a standard symbol for the battery. Well, it has 2 electrodes, and one electrode has a high potential relative to another electrode. And now we can connect a capacitor to a battery using wires. And now, what do? We move the plates apart. So this is, if something changes, we always can draw 2 pictures. This is what we call before something had happened, before. And how would you draw a picture for after? Well, same battery. But now the plates are moved away from each other. And now survey says Mostly correct. Yeah. When a capacitor is being connected to the source of the voltage, that source of the voltage is responsible for the voltage across the capacitor. So wherever the voltage here is, equal to very soon we will give a different name for the same thing. The same voltage will be across the capacitor. When something changes, the first question we always should ask is, what doesn't? What remains constant? What remains the same? And in this situation, this. That's the first part of the reasoning. The rest is, well, almost automatically is derived from this. We also know that charge, voltage, capacitance are related. How? By a definition of capacitance. We also know that capacitance is related to features of a capacitor. For the parallel plate capacitor, a dielectric constant, another constant, area. So when the distance between the plates increases, how does it affect the capacitance? It decreases. It's inversely proportional. And when now these three relationships together tell us what should be happening to the charge. One factor in this product remains constant, and second decreases. So the whole product should decrease, the charge should be decreasing. Hence, any questions? Well, I think we have the answer here. And now we, of course, can ask extra questions. What is happening to other variables? For example, electric field, energy. So for electric field, we have two different equations. One relates electric field with a charge. Second relates electric field with voltage. So it is handy to know both. Inside a parallel plate capacitor, when it's charged to a charge Q, electric field on one hand is related to a charge and area. On another hand, it is related to the voltage and distance. In this situation, it doesn't matter what equation we want to use. Delta V remains constant, constant, constant. D increases. Charge decreases. Area, do we change the area? Constant. Well, it is air-filled capacitor. This is just a one. Air, a vacuum. Or technically any gas. We need a real dense material with a high dielectric constant to affect electric field. So what is happening to the electric field? Decrease. Yeah. Hence, goes down. And for the energy stored in the capacitor, we actually have three different expressions. 1/2 Q delta V. 1/2 delta V C delta V squared, 1/2. what I want to do. Q squared over C. Yes, Q squared over C. Which of these three expressions would be the least convenient to use? It's a very important question. We always have to make a choice. And it's not right or wrong choice. It's a less convenient or more convenient choice. And the answer is, if an expression has variables which change, both variables, all variables change, we cannot use it. We'll always need an expression which has one variable which doesn't change and another changes. So this one is not good because, by the way, I didn't ask how the sound. When I look at you, you always look away. How is the sound? I need to know if I need to fiddle with the volume. On a scale from 1 to 5, the quality of sound, that's fine. Thank you. So the charge changes, the capacitance changes. So we cannot really use this. But here, the voltage remains constant, the capacitance decreases, so the energy, I can also add this from the last slide. So the energy should go down as well. Constant, decreases, decreases. Any questions? It's a standard reasoning. We're going to do a little bit more examples, but every time we have to ask two questions. First question. What does not change? And second question, which equation has only one changing variable? That's it. All right, now a different situation. We use the same capacitor. We connect it to the battery. We charge it up, but then we disconnect the battery. So please take a minute, process it, because I'm going to switch. What is happening to voltage? That's it. If we have any quantity, any variable, it might remain constant or increase or decrease in value. So these are the only options we have to choose from, right? And let's see if I can fit the camera. Yes. All people who develop software think we are stupid. I don't want to enlarge it for the whole screen, but it does it automatically for me. I know the size I need, this one. Come on. All right. You can read the keyword disconnected. So what I have here is not a battery, but just power supply, because I want to charge it to a higher potential so we could read numbers easier. Where should we read the numbers? Well, we can read them here. This is a very sensitive multimeter. And also, I connected to a display multimeter. These numbers are different, but all we need to see how they change. This is the capacitor. So the capacitor is connected directly to this kind of electroscope, and it's connected to this. Is it on? No. Now it's on. So I can move the plates apart. All right, it's in the screen. Now I need to connect power supply and turn it on. And turn this on. So you can see certain voltage. And the first question was about the capacitor when it's been connected, remained connected. So if it's remaining and I move plates back and forth, nothing changes. What I really want to do now, it's 200 volts, I don't want to touch it. So now we can disconnect it. So it's 0. Yeah. Now I turn it on. Now I charge it, remove. And if I move them closer, voltage decreases. If I move them apart, the voltage increases. In our question, it was disconnected, and the distance was increasing, so the voltage should increase. But of course, there is a way to figure it out algebraically. That's what you should have done already by now, right? Don't touch it. Unless you really, really want to. All right. What is the first question to ask? No, that's not the first question. What is the first question? What does not change? So, in this situation, when we have capacitor charged, and then, so there is certain voltage across it, a certain voltage. Well, let's say this is a positive plate, negative one. Nothing works on Tuesdays. And what variables can we list to think about? Charge, voltage, capacitance, distance between the plates, area, electric field strength, energy. Did I forget anything? Well, technically, it could have been dielectric constant if we adding something in. So out of this list, there's one variable which is definitely constant. You tell me what it is, and that's it. Everything is very clear. What is that? What do you think? All right, two variables. Yes, we do not change area. That is correct. We could have, and that will be actually the next question. Right now, we just move plates apart. What else? What do you think? What? Three variables. Or else? Not related to how capacitor is built, but related to what is happening to it inside it. Exactly. Thank you very much. And why? Because electrons don't have any room to escape. We cut the wires, well, disconnected the wires. So no matter what is happening to the plates, the number of electrons missing or extra electrons remains constant. We know a charge is equal to, well, a positive charge is equal to the number of missing electrons times the elementary charge. And a negative charge will be equal to negative this. This is the number of extra electrons times the elementary charge. We know that. If the number of electrons doesn't change, the charge doesn't change, remains constant. That's it. Now we just throw in exactly the same equations and just see how variables work out. For example, Q, well, first of all, probably we should start from C. Still same change. If it goes up, this goes down. Now, Q is equal to C times delta V, but we need to use it to say something about delta V. The numerator remains constant, but the capacitance decreases, delta V increases. So as we saw in this situation, when we moved plates apart, the voltage was getting larger and vice versa. What about electric field? Well, that's one equation we could use, but would we? In this equation, both variables change. So it is not a convenient equation to use. All right, moving on. What else do we know? The charge remains constant. We do not change the area. That, well, and K equals 1. In this situation, just a 1. So it came from our approximation that plates are very, 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 very large, huge. So the distance between those plates shouldn't affect electric field strength if we keep the same charge, the same area. And last one, energy, right? For the energy, what equation would you choose to use? Well, we can use this one, 1/2 Q delta V, because Q remains constant, delta V increases. Moving on. The answer now, that is a new problem. How do I know? I can read. So a capacitor is connected to a power supply. We do not change the distance. We are inserting a dielectric. All right. So in this environment, this experiment is really, really tough to do. But we have an app which can help. So what's happening here? Well, we switch to a dielectric, and well, we can turn on all meters here if we want to. Measure voltage, measure energy, everything. And what's going to happen when I am inserting a dielectric? By adding a dielectric, we're changing capacitance, of course. So I can remove it. Can I? Yeah. So you see, it changes the number of charges. Why? when we change capacitance, but capacitor remains connected to a battery, so it either absorbs more or push away charges. And in this situation, it's not a question for the Weber sign. Let's just see what's happening. First, we need to know what remains constant. And the key word is this. When capacitor remains to be connected to the battery, what should definitely be constant? What do you think? What does not change? Does not change in this situation. What? The Q would have changed. What doesn't? What do you think? Anyone from this table? Just shout. Voltage. Why? Because it's not up to capacitor. It's up to the source of the voltage, up to the battery. So this, no matter what is happening, this variable is responsible for the voltage across the capacitor. It should remain constant. So this is a picture for a capacitor before we inserted dielectric. Now we can draw a similar picture with a dielectric. So still the same voltage. Yep. What about C, capacitance? It should change. That was equal to 1 times. And now it is equal to, well, that's what we call a capacitance of air field capacitor. Yeah. And now it should be equal to kappa and this variable is always greater than 1. So the capacitance goes up. You can ask why is it always greater than 1? In a minute we'll talk about it. But for now, it's just a fact which we use to figure out what is happening to all other variables. So the capacitance goes up. The voltage remains constant. How does it affect the charge? The charge should go up. Any questions? Now you can throw in all other equations and finish the analysis in a way we just have done. Now, if we disconnect the battery and then insert the dielectric, what should be happening now? Well, what is the first question to ask? And what does not change? If we disconnect it from a source, what does not change? The charge. That's it. That's how we reason every time. The first question, what does not change? If capacitor remains connected, voltage does not change. If capacitor is disconnected, charge does not change. In this situation, Q should remain constant. However, as we know, still capacitance should go up. Still. Then the relationship between Q, charge, capacitance, C, and voltage, always given by the same equation. So I want to switch. Okay, so delta V will be equal to Q over C. Q remains constant and C increases, so delta V decreases. Any questions? And let's talk what's happening to electric field. What do you think will happen? Well, again, for electric field, okay. For the electric field strength, we have two equations. We can use this one because D remains constant. Yeah. We do not move them apart. We just fill it up with dielectric. So distance remains constant. The voltage goes down. That means electric field should go down. And now this picture tells us why. When we don't change the charge on the plates, but adding a dielectric, why? The net electric field decreases. Because remember the experiment with a plastic bat and piece of wood? Electric field polarizes molecules inside. So if we insert a dielectric, that external electric field polarizes molecules. And the dielectric now has a surface charge. Surface. Close to the positive, we have a thin layer of negative electrons. Close to the negative plate of a capacitor, we have a thin layer of positive charges. But those layers also create electric field. And that electric field always will be opposite to the external. So the actual net electric field always is less than before we inserted the dielectric. That's why, well, first of all, now we can say what is kappa actually equal to. This is an official definition of a dielectric constant. Electric field in vacuum or air divided by the actual electric field. And that's why it is always greater than 1. Because when we insert a dielectric, again, when charge remains constant, the net electric field decreases due to internal polarization of a dielectric. Any questions? I think that's really cool. We can prove with simple reasoning that every dielectric always should have dielectric constant greater than 1, bless you. If we inserting a dielectric, we always increasing the capacitance, always. You look like you want to move closer. You can move closer. All right. This experiment doesn't require a camera. You can see probably, well, actually, I closed it, but I can open it again, I guess. All I have here is a very large capacitor. It's not just large, it's very heavy. And a strong power supply, but I also have a standard battery and a small capacitor. What's the difference? Well, the storage, this can store 8 microfarad, but it can sustain very high voltage, up to 5,000 volts. And this one, only up to 50 volts and 60 can't read it, 60 microfarad. So I use just a regular battery, and I want to charge it. How do I do it? I just connect my glasses, a plus to a plus, a minus to a minus, and I should wait a little. It takes time to charge a capacitor. And now this battery getting a certain amount of energy. What's going to happen if I try to shorten the electrodes? Not using my fingers. I don't want that. See? You can see a spark. Why? A quick release of energy. And this is just 9 volts. Already gives a spark. Now I want to use 5,000 volts. What do you expect to happen? Why do you think I have this? I will tell you when you should close your ears, cover your ears. All right, first things first, it's very dangerous. I've been almost killed once. 5,000 volts. Nothing. But in the morning, this demonstration helps to keep people awake, so I have to do it. Oops, this power supply doesn't work. Okay, it does work. I can see how voltage increases gradually from 0 to, it actually takes time. 5, even more, 6. All right, first I need to disconnect it. Turn it off. Now I want to shorten it. Now you can cover your ears. Now let's see what's going to happen. I actually should have some residue charge. Yeah. All right. Now it's safe to touch it again, but only now. What's this about? If you calculate the energy, well, this calculation tells you what energy does it store if I would use only 4,000 volts. In reality, I used 6,000 volts. So actual energy even higher, but still it's only 64 joules, or like 70 something. Why is it dangerous? If, you know, if you take 1 kilogram weight and you move it up to 10 meters, that's going to be 100 joules of potential energy. It's not really dangerous, well, unless it hits you on the head, but the answer is, it's not just about energy, it's about how fast it's being released. It's about power of that spark, like lightning bolt. When electron travels very slowly through the tissue, like you're touching the battery, it doesn't really affect the tissue, but if you have many, many electrons traveling through a tissue very quickly, it's like using a machine gun, so it can damage the tissue. But it's not always a bad thing, as you know. Yeah. Sometimes it's a good thing. It can revive the heart. The same principle. You just have to know what voltage to apply. But also, this is a demonstration of importance of moving charges. And that's our next topic. When we have a large amount of charges moving in the same direction, we call it electric current. If we have a large amount of fluid traveling in the same direction, we call it just current. Yeah? So to move on to the new topic, first I want to ask you this question because it's about moving charges. Here you have two plates. They generate electric field between. This plate has a high potential, low potential. This particle is an electron, and we release it from rest. We let it go. How would it move? And this is probably a very rare occasion when you need to think a little. Plus, it's very similar to one of your homework problems. If you let an object go from rest, the direction of its motion from rest to not rest anymore should be the same as the direction of the acceleration. But acceleration is provided by the force, well, net force. In this situation, we can neglect gravity, no strings attached, no friction, only electric force is acting on it. Electric force, charge, and something else is related. What? Electric force, charge, and what else? Related by one equation. What equation should we write as a connection between electric force, a charge, and electric field? Exactly. However, the electric field also is related to potential difference in space. And the relationship is given by two rules. One is about direction, which we should use here. Second is about angle. So I want to see what you've answered. This is the question. Number four. The most popular answer is number 2 to the left. Yes, it's true. Why? Because there is a very simple answer for that, which I didn't mention. I deflected your attention. Yes? That's too complicated. There's even simpler. Yes? Exactly. Positive charges attract negative charges. If you have a positively charged plate, you can make a safe assumption it has positive charges here, some negative charges here. But still, the logic, which I also mentioned, works. What is the direction of electric field? It always goes from plus to minus, from high potential to low potential. That's electric field. How is electric field related to charge and force? This expression is just a definition of electric field. And for a negative charge, these vectors must be opposite to each other. So if we let it go, it starts moving to the left. Now imagine it's not one electron, but billions of billions of billions of electrons inside a conductor, like inside of a wire. All we need to do is to generate potential difference between two ends of this wire. Make one potential higher than another. In that case, there is electric field immediately generated inside that wire. That electric field exerts a force on all electrons. All electrons, of course, travel chaotically due to, well, just average kinetic energy due to temperature, but also after electric field is being applied to all of them at the same time, they all start drifting, traveling on average in the same direction. So let's say this end has a higher potential, this end has a lower potential. So electric field points from high to low. Electrons are negative. Force acting on each electron points to the right. They should start moving to the right on average. And people say, if electrons move to the right, electric current points to the left. You can say, why? It just happened. People didn't know about electrons at the time. So they thought some kind of a positive charges would have been traveling in wires. That's it. So if the question is about a direction of electric current, we should think about fictional positive charges traveling inside. Or we can just say, in a wire, electric current should point in the direction of electric field. That's it. Yeah. Or you can imagine a fictional positive charge which doesn't exist. It's fictional, it's only in your mind, so don't stick to that too often. But you can imagine you have a positive charge here, it would have been traveling like that. That's the direction of electric current according to an agreement, a definition, a convention between everybody. All right, let's do the problem. Electric current, blah, 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 blah. What does M mean? Meters? Mass? What does it mean? Milli. So, you see, they don't say electric current. They say current, like they don't say electric potential. They say potential, but we need to know that slang. We need to know that in this problem, it's not about current in a river. It's about traveling electrons inside a circuit, inside the battery or something else. Is equal to 0.17 times 10 to the negative third amps. What is amp? Well, thank you, you asked. That equation you've seen already before, like several minutes ago, is an official definition of electric current. It's the amount of charge traveling every second. That's it. So a coulomb over a second, that's what people call ampere. And on another hand, that should be equal to total charge traveling over a certain period of time. What is the period of time? 1 hour. What is wrong with that number? It's not in seconds. So we'll only need to convert time into seconds, solve it for the charge. Time times current 3600 times 0.17 times 10 to the negative 3. That's supposed to be coulombs. Someone should tell me the number. Someone with a calculator should tell me the number. So I could write it down and blame that person if the number is wrong. That's why you moved away, right? Yes? Cannot hear you, please. 0.612 coulombs. It's actually a large number or a charge, you know. Elementary charge 1.6 times 10 to the negative 19th. So it requires a huge number of electrons to travel. And the next question naturally is, how many electrons did travel? Well, we just needed to use that relationship between the charge, the number of electrons, and the elementary charge. So this is what we can calculate immediately in 1 hour. So in 1 hour, the charge traveling through the wire is 0.61, and the elementary charge is 1.6 times 10 to the negative 19th, and that will give us the number of electrons traveling in 1 hour. So someone can tell me that. And if we want to calculate the number of electrons traveling in a second, well, we have different options, right? 1 hour. We have different options. For example, I know how much charge travels in a second. Why? Because that's what the current is. Amount of charge traveling per second. So for 1 hour, for 1 second, 0.17 times 10 to the negative 3 coulombs travels every second, divided by 1.6 times 10 to the negative 19. That will be the amount of electrons traveling per second. And again, someone can tell me a number if you want to. Questions, please. All right. You don't want to tell me a number. I'm moving on. So, in reality, things are a little bit more complicated. This picture doesn't show atoms, which also, of course, exist. Without atoms, the net force acting on each electron, well, would be not equal to 0. That's what's important. So acceleration wouldn't be 0, and electrons would have been accelerating, speeding up forever. But that's, of course, not is a case. Actually, under regular conditions, if we flip on the switch, electrons travel very, very slowly, slower than 1 millimeter per second. Why? Well, because when they collide with very heavy atoms, they bounce back. They lose some energy due to that. Atoms start moving a little bit faster, warming up. So we call this phenomenon resistance. And what is happening with each electron? Electric field makes it move a little bit faster. It collides, bounce back. But electric field picks it up, again, moves again faster, and it bounce back. So on average, they will travel very, very slowly with a constant velocity. And that velocity, of course, depends on how much strong electric field is. And electric field strength depends on potential difference. If we apply a high potential difference, we generate electric field, and it results in higher drift velocity. And this relationship between how much voltage is applied and how fast electrons travel, which is basically a current, this relationship has been experimentally derived, again, more than hundreds of years ago by a physicist with the name Ohm. That's why this relationship has a name, Ohm's law. He just proved that electric current and voltage applied proportional. More voltage, higher current. Hundreds of years ago, it was very difficult to prove, actually, because they didn't have multimeters. It was very, very difficult to measure electric current, even potential. So it's kind of amazing it was possible to do. The coefficient this constant depends solely on the properties of a wire or a device, a resistor, a bulb, or some. So it depends on how long it is, how wide it is, what kind of atoms it's built on. It has a name, resistance, the resistance of this device, the resistance of this bulb, the resistance of this coil. And the resistance depends on the length. The longer the wire is, the more resistance it provides, which is natural, more atoms. It's inversely proportional to the area. Again, wider area, more room for electrons to travel, less resistance. But also on internal properties like the size of those atoms. And this coefficient, Greek letter rho, is not the density in this equation. It's resistivity. It is measured, for example, okay, I'm going to move it back. Right now, if you want to, you can go online. And there is an applet which tells you the resistance of any wire of your choice. You can just choose the material, set the length of your wire, set the diameter, and read the number. That's it. How does it do? Well, it uses this equation. I just want to show very quickly how nowadays we can use different devices. Like this one. This one is good because it measures lots of things. It doesn't measure capacitance, but it measures voltage, electric current, and the resistance. Right now it is set to the resistance. This symbol is a unit of resistance, ohms. People used to write OHM. Now they write a capital omega, resistance. And how do I measure resistance? Well, I need to connect something like this coil, for example. It has lots of loops, so it's actually very, very long. Oops. Okay, I'm going to start from this one. So one should go to 1. It's a ground, so there's always a ground. And another should go into what? Well, this says A, so it's for measuring electric current. This says V or omega, so it's for measuring voltage or resistance. So I can just plug it in. And it takes some time to get the equilibrium, 1.5 ohms. It's a very low resistance. Oops. If I double the length, what should I expect? Yeah, I have to connect. This connection actually has a name. How do we call it? If one after another. Series, exactly. So I doubled the length, and I see the resistance goes up. Well, not exactly doubled, maybe. Just out of curiosity, a regular flashlight bulb. See, it's not connected to anything. This measures resistance internally. Yeah, 7, 8 ohms. That's a standard value for a regular flashlight bulb resistance. And two together, what should you expect? It's nothing, because I need to connect these bulbs. I have to complete the circuit. If the circuit is broken, of course, nothing can be measured. But if I connect, about twice of that. Where is the resistance in a bulb? In the filament, of course. Wires, as you saw, practically have no resistance. So every wire for us is resistible, not irresistible. Yeah? And has no resistance. And let's just do an example. All right. Calculate the resistance of 10-meter long wire made of copper with a square cross-section. Square, it's easier to calculate area. That's it. So this is our equation. The resistance equals the resistivity. This number comes from search. It has been measured. What is it, actually? If you look at this equation, if you get a cube, one by one by one, that cube will have the length equal to 1 and area equal to 1 meter squared. So the resistivity is just a resistance of that cube. That's how you can measure it if you want to. I would measure resistivity of a cube of gold. So what do we do? 1.678 times 10 to the negative 8. That's the resistivity of copper. How do we know? We do the search. 1 point, oops, come back. 678. Copper has a very low resistance. -8. This is the unit, which of course comes from that equation. Times length is given 10 meters divided by area. Well, area is the only tricky part in this calculation. We cannot use millimeters, right? So it should be 0.001 meter times 0.001 meter. We can see meter and meter getting cancelled, meter and this meter cancelled. The result is just ohms. Wherever it is, you can calculate the number, write it down, tell me. Any questions? So please tell me the number. I see people actually calculating it. So, anyone? Point? Well, in this situation, so 10, -3, -6 make it +6, 7, -8, 7, -1. So we shift a decimal point one place to the left. Question? Since you don't have a question, I should have. Please just calculate. Bless you. What do you think potential difference between the ends of this wire should be equal to? Now we need to combine a definition of electric current and the Ohm's law. That's it. Normally all problems are very straightforward. The only thing to keep an eye on is units, right? So we have a wire with a given resistance, 10 ohms. And if we wait exactly 1 minute, we know, someone told us, someone we call multimeter, told us that 360 coulombs of charge traveled through this wire in 1 minute. But we know electric current has been generated by a certain potential difference If we didn't have any potential difference, we wouldn't have any electric current. So that's what we're looking for. And then you can pick your number. The trickiest part is what? Converting minutes into seconds. That's it. If you don't forget to do that, what do you get? 60. You should get 60. Yeah. Let's see. You have solved problem in physics absolutely correctly. That should boost your confidence, right? You feel better, more confident. Now, this is what we can do immediately. The voltage we are looking for should be equal to the charge over time, charge per second, times the resistance. We have 360 coulombs over 60 seconds times 10 ohms, 0.0660. Very clear. Any questions? Another situation, I'm going to give you a minute to read it. Here, the only issue is what to do when we have, by some weird reason, two batteries. Now, every battery has two electrodes. One electrode is positive, has a higher potential. Second is negative. Same this one. And I have only two options. I can connect same electrodes, like minus to minus or plus to plus, or I can connect opposite, plus to minus. It's up to us. But one connection will be wrong, practically wrong. Why? Because they will be canceling each other. We don't want to do that. So in this situation, of course, we should assume that batteries are connected correctly from a practical point of view. And correctly means one after another. First battery. So would be this a correct way to connect the batteries? No. This battery, well, I like electrons. So this battery on the left would be moving electrons. That would have been velocity of electrons. So this battery would be moving electrons to the right, but this battery would be moving electrons to the left, so they would actually cancel each other. So not good. So this is what we want to do. Connect opposite electrodes, a plus to a minus. And now we just have a bulb. Now, in engineering and in physics, this is a standard symbol for a bulb, a circle with a cross inside. I don't know why. And now we just know that if each battery supplies 1.5 volts and we are adding them up together, that's all we need to know. The voltage across the bulb, this voltage for the bulb will be just 3 volts. And now we know voltage, we know current. We can use the Ohm's law to calculate the resistance. 30 over 4, right? Just want to make sure. 7.5, yeah. Any questions? No? I do have a question. Several minutes ago, we saw this example. Two, well, we call them elements, devices, resistors. This is also a resistor. This is a variable resistor. We can change the resistance. And here I have two of those devices, elements, resistors, connected. In series, as we know, the name of the connection doesn't depend on what devices do we use. Capacitors, resistors, coils. And if I want any current travel through this, I have to connect it to the battery, and I have to complete the circuit. Now, there is a current, electric current, traveling in this circuit. In which direction? Well, I gotta check the electrodes. And I can see this is a plus, this is a minus. You cannot see it, but I can see it. Plus, minus. What does it mean? It means electrons actually would be traveling from a minus away. Those fictional positive charges would be traveling from a plus away. And that's what we call direction of electric current. So in this circuit, we should say electric current travels like this, or points like this. And what did you say? What do they have the same? Traveling per second. How do we call it? Current, exactly. This is basically a kind of law of conservation of charge in this case. The same amount of electrons should travel everywhere. They don't have any room to escape. We don't adding extra electrons. So if 1 coulomb per second travels here, 1 coulomb per second should travel here, 1 coulomb per second should travel here. They should have the same electric current. See this guy? It looks sad. Let's make it happy. So, this is our circuit. This is the voltage provided by the battery. Of course, across each element we should have its own voltage, and I prefer my symbols, delta V for the voltage, not just V. And the electric current traveling through the circuit is the same everywhere, which means we can apply the Ohm's law. Well, delta V1 is supposed to be equal to current times the resistance of the first resistor. Delta V2 should be equal to same current. And now we can ask the famous question, what single resistor could we use to replace these two? How would we call that resistance? If instead of using, this is a standard symbol for a resistor. If instead of using 2 or 3 or more, we want to use only one, how do we call it? Equivalent. We call it equivalent because we want this resistor experience exactly the same electric current when it is connected to exactly the same battery. That's what this word means, equivalent, in this context. So this is the relationship we can write for the equivalent resistor. Well, as we know from the past, okay, I might use it later, so this voltage plus this voltage should give the total voltage. That is the connection. So we can write it down. We can write the Ohm's law inside this equation 3 times. Physics is done. But now we can do some simple mathematics. We can cancel the current because it's the same. The result is this. 4 resistors connected in series. If we want to replace them with a single resistor, the resistance of that single resistor is just the sum of individual resistances. That's it. Now I'm going to skip it for tomorrow, and I'm going to point at this slide. We just have it proved. And now, of course, we should talk about another situation. Resistors connected in parallel. It's not a question for the Weber sign, but we should think about it. What do they have in common? And since these elements, and it doesn't matter, capacitors, resistors, connected to the same voltage, to the same battery, they have the same voltage. So here, electric current splits. It travels. Again, you can look at actual electrons traveling like this. You can look at fictional positive charges traveling like this. Doesn't matter. Here, at this point, the current splits. How does it split? Maybe evenly, maybe not. It always depends on actual values of these resistors. The splitting point has a name, a junction. And for the junction, this equation always works because it is a law of conservation of charge. If we add how many electrons travel here per second and here, we should get the original number of electrons. And then they combine together. This equation has a name, a junction rule. In general, it could have more wires, more currents, but still, the junction rule is just a manifestation of the law of conservation of charge. It splits and then combines together. And now, so we can use the junction rule for any number of devices connected in parallel. And I'm just going to point at it because I don't have time left. This is what is happening. If we apply the junction rule correctly, and if we write the Ohm's law for each element, for the actual resistor number 1, or the actual resistor number 2, and then for that single resistor we want to use to replace all these resistors, but to have exactly the same voltage and current in the system. That's what we're going to do. This is the equation which we should use to calculate the equivalent resistance of that single resistor. We should use to replace any number of resistors connected in parallel. And we've seen this equation just for capacitors. But what is the difference? We used a similar equation for capacitors connected in series. Okay, technically right now, from this very point, this is just a review, some helpful analogies people can use between electric current and the current of water traveling through pipes. Electric current basically is a charge flow rate. We've talked about volume flow rate in PY105. Similar variable, but only for electrons, not for water molecules. And potential is, electric potential is an analogous variable for pressure. Pressure inside pipe changes and it makes water move. And potential difference is the equivalent of pressure difference. And pressure difference related to force in pipes. And potential difference is related to force in wires. Very similar approach. These are all equations we just have learned. And that's it. You're ready. I feel it. You are ready to finish the whole homework. There will be one more new equation tomorrow. And I'm done for today. And that lady who left, she will regret it. There was a lady who, she left just a minute ago. But you know what I ask you to do. When you see this, you know what I'm asking you to do, right? I ask you, before you leave the room, approach the bench, find your name, and leave your signature.
Yesterday, I think
I didn't do it yesterday. I do it randomly. When I remember, I do it. When I don't do it. Yes.
Can I ask you a question?
Yes.
I screwed up personally, and I didn't complete my part one on time. I thought it was due. Thank you so much. All of
I have not read any emails yet, so I don't know what you're talking about. So you can just tell me.
I would like an extension on homework part one for even a few hours. I didn't complete it, and it's completely my fault. But I would really like.
I will give you an extension because actually I plan to give an extension to everyone anyway, and you just reminded me that I didn't do that.
Thank you very much.
Thank you.
Hi.
Hi.
I didn't realize I have to have you for 105. Last week I didn't sign the hour.
When?
All last week.
Yes, well, last week.
Yeah. I answer all the questions on work assignment. I'm always here. That's
All right. You should be all set, but just in case, please send me an email here with what you just said.
okay, yeah. Thank you.
Yes.
I got to ask this note that I was looking through my notes again, and you see how here you wrote 0.17 MA is the I, is the current. You
Yes.
then use that value to solve charge. You plugged it in as
For
charge.
1 second.
Why do you use it for 1 second if that's the charge?
See?
Does charge equal
We had two questions. First question was, how many electrons travel in 1 second
and then in one.
and when in 1 hour? So when I need to know a charge traveling per second, that's what current is by definition. Electric current is equal to a charge traveling every second.
Oh, so basically the charge.
So this is 0.17 milliamps divided by 1 second.
Okay, divided by 1 second. Okay, so when you say per second, you're just saying
Yep.
you could use the I and divide it by seconds, and that
Yep.
would be the charge.
Yep.
Okay. Thank you.
Sure. Yes.
Hi. I just wanted to make sure I can I know I'm supposed to email you, but I'm taking the test on Tuesday instead of Monday.
You told me, right, about
Yes.
it? Yeah,
I'll
yeah.
just remind you.
Yeah, thank you.
For Monday, should I just not come to the class time period, or
What do you mean?
well, are they taking the test during the class time?
Yes.
So should I not come for that?
That's it. So, again, so you still have time to study. I thought you will be back on Monday.
I get back Sunday night at 10 o'clock.
All right. Did I do it?